Welcome back, guys. Today we'll be talking about modeling data in organization. So today we will see our first entity relationship diagram, and also today during the class we will be covering first assignment of your homework. Homework is posted. Homework 1 is available. Please start working on that. It's very important not to wait until the last moment and get started. We'll talk more about homework later on, but today during the class, we will cover the first question of homework 1. So let's start. A little review of the last class. Data. What is data? Data is can be in different formats. It's a stored representation of the objects, events, anything that we're trying to save or store in the database. There is different data types. If you remember, we talked about those in last class. Can be integer, can be different types of numbers, decimal, characters, varchars, which means variable length characters, can be date, time, can also be videos, audios, but those type of data are stored in big data databases. Also we talked about information. Information is a data processed to provide us more details or increase knowledge, so we can use the data, meaningful data, to make informative decisions. And database is an organized collection of the logically related data. Metadata. Metadata is a very important term. We will get back to this term several times during this course. Metadata is data about data. So that is a set of rules that define specific data stored in the database. We also talked about evolutions of the databases. We spent a little bit of time talking about different file systems, which represents collection of the files used by different organizations. File systems are, believe it or not, still widely used, and we talked about that too. Well, file systems represent multiple problems. We talked about program data dependence, which means that specific program depends on the data in the file. We also talked about program structure dependence. That's when the program access depends on the structure or the set of files or specific file. Talked about data redundancy. Data redundancy means data repetition, where multiple data sets of the same kind stored in different places. Also talked about limited data sharing, long processing times, and so forth. When we talked about data redundancy, we talked a little bit about different anomalies. Hope you remember those anomalies. Those anomalies are tightly coupled to procedures or to actions that we can make to data in the files. So there is delete anomaly, insert anomaly, and update anomaly. So that represents the actual insert, update, or delete actions to data. We talked about structural data dependence. We already touched it when we talked about file systems. We also talked about database management systems and its components. It includes software, hardware, people, procedures, data access language. And data access language in the duration of this class for us is going to be SQL. SQL is a language widely used by Second, I'm trying to see if I'm recording it right. Yeah, so SQL language is a language widely used by relational databases. When we talk about big data databases, they do have their own proprietary language. And at the end of the lecture, we did talk about different types of the databases. Those include single user database, multi-user database, data structural databases, databases that store unstructured data, and so forth. So today we are going to expand a little bit on the last class, and we will talk on how organization stores data. We will be talking about data models today and why data models are important. We're gonna look briefly on evolution data model or the data models. And for the evolution of data models, we will need a concept of abstraction. For those of you who took programming classes, you guys probably know about abstraction, but for those of you who don't, we will discuss it today, what abstraction is and why it's important to understand the abstraction. We'll be getting to this term abstraction multiple times during this course, so it's important to understand it. So we will learn in details two different data models. We will learn about relational data model, and that's what will be covered in your homework. First homework, that's question 1 of your homework. We'll learn about how to read relational data model, how to connect different tables or relations in relational data model. And then the rest of the class we will spend on entity relationship data model. And its representation, entity relationship diagram. We'll also look at a couple of examples on how to build entity relationship diagrams. So all of that will be preparation for our next class, where we'll be learning entity relationship model in more details. All right, so what is data modeling? Data model is a simplified representation of a complicated real-world problem or scenario or dependency. And data modeling refers to the process of creating the actual data model. It's very important to understand that there is no final data model. All the data models are work in progress. Creating data models is iterative process that takes multiple attempts and updates to have data model available to create logical design and future database based on. Data models breathe and live in things. Just like I said, they're updated very frequently as business changes its rules. Data model must affect those changes properly to be able to address those changes in the database. Importance of data models. Data models are the most important communication tool in business. So when business brings up some requirements, engineers or designers create data models that helps business in the future to communicate with between different departments. Data model is also a very first technical step in system development. Below are the steps that are part of system development. System development includes system requirements gathering, then creating data model, then database creation and system development, and further down, testing and deployment to real world. All of those will be covered in MIS3 06 class, which some of you might take in the future. So just remember that a data model is one part of the larger process called system development. And you can create a good database without having a decent model, because again, you can have system without a design, without a good design, right? Similar to the database. Data model is the first step in creating a database or database design. And subsequently, you can't build a good system without a good database. So, good system, good functional system, fully depend on how good your database model is. And system scalability is also based on data model scalability. Scalability is an ability to store more data within a system. Scalability can be horizontal when we just add more data to the certain system, a certain database, or it can be vertical. Vertical is scalability is an ability to add more nodes to the existing model. Okay. So, a couple of important terms here: data model creation, system scalability. Please read through the slides. I have more explanation in the notes on the slides on database and system scalability. It's very important to understand the difference between horizontal and vertical scalability. Um, so we're gonna look a little bit about the case study. So what is a bad data model, and how data model is how it's important is to have a good data model in system development. So let's look, you guys probably all remember about healthcare.gov. So the idea behind the system was to provide access to affordable healthcare insurance. That was a representation, it was a technical implementation of Obamacare. So the purpose was fantastic, to make sure that all US citizens have insurance. Well, as any, you guys can read a lot online about healthcare.gov, but as any system that was initially designed really good, but then it was not enough time spent on actual implementation, the system had multiple issues. So, first of all, data model behind the system was very complex. Data model was not designed to support both vertical and horizontal scalability. As a result, it was performing really poor. There were multiple data integration problems where data model didn't work with different system providers that must be integrated within the system. Data inconsistencies, we know what data inconsistencies are. We did talk about that. That's when the same data is not updated in two different interacting system at the same time. This system also had various security concerns, which is a little bit out of scope of the data model, but key point here. The major issue with the healthcare.gov and its implementation was its bad data model behind it. Interesting thing. So, when they put healthcare.gov into production, they expect to have millions of accounts created in this system. So the moment they make the system available to users in the first day, they expected to have up to 2 million accounts. How many accounts do you guys think were created? You can put a pause on this video and make some educated guesses. All right. Ready for an answer? During the first day, I think they created 8 or 4 accounts. Next day, they created, I think, up to 800 accounts. But again, this system as a whole uh, failed miserably because of the issues with the data model. So as you can see, data model is a very important step in system development. And just like we talked before, you can't create a good database without a good data model, and subsequently you can't have a good system without a good database behind it. There is more examples of bad data model. You can read about those if you're interested. You can you can open the slideshow and look at the links in the slideshow. Okay, so we talked about data models. We talked about the importance of data models. Now we're going to talk about different types of data models, but we will look at those data models types from a data abstraction point of view. So data abstraction is a very important term. It was initially introduced by ANSI. ANSI is an organization that is responsible for different formats, templates. So based on ANSI definition, abstraction refers to a process of simplifying complex idea or objects into leaving complicated details behind. So, for example, um, Google Map. Google Map represents an abstraction of the actual maps, so actual roads, actual buildings. So if you look at the Google Maps, you probably would only see the data necessary for users to be able to navigate from place A to place B. So, based on the data abstraction, there's 4 different data models based on the data abstraction. Those are external data model, conceptual, internal, and physical. So here is a representation of what we just talked. So um, those are data models in organizations. So we are talking here about external data model that is used by end users. Conceptual model is a view where database designers live. So all the design concepts and the main data model is developed on the conceptual model level. Further down, we have an internal data model. Internal data model is the model that has the actual database on it. So that is a view of your database management system. And on the very bottom, we have a physical data model that has the lowest level of abstraction. So this diagram represents different data model based on the degree of data abstraction. So for example, on the external model, we have the highest data abstraction. So end users do not need to know how the database looks on internal models. They don't need to understand where the tables are stored. They don't need to understand what hard drive or what actual server the database sits. The only thing they care about is to have access to retrieve data from the database. Okay, so it's the highest level of abstraction. Down low, we have a conceptual data model that has a little higher level, a little lower level of data abstraction. So it conceptual data model needs to know a little more about the actual database, but still, it's a very high level of abstraction. And going down, we have degree of abstraction lower and lower up until we get to the physical model, which is the lowest degree of the data abstraction. We are going to talk about two very important concepts here, logical and physical independence. Logical independence exists between the conceptual data model, where we create first design for the database, and actual database view. So, logical independence means that you can modify logical structure or schema of the data without affecting conceptual data model or applications that are used in the database. So your logical independence lives between conceptual model and internal model. So in other terms, for example, we can modify database tables. We can modify how we store the data without changing the programs or software that uses this data. Okay. So an example, if a new table is added to the database, the existing table is modified, we don't need to change the application programs that are using this data. That is logical independence. Okay. Physical independence is a concept that allows us to make changes to the physical structure without affecting the logical schema or internal model. Physical independence is much harder to achieve than logical because database systems in the current market, they are designed for a specific data storage requirements. So for example, if your current system is if your current database is a SQL server and you're trying to say switch your system to Oracle, you will not be able to use the same file structure. So physical independence is much harder to achieve. So an example would be when you move from one physical storage to another physical storage of the actual files, your the way you access the data or the way you query the data is going to remain unchanged, which is again very difficult to achieve. So let's look at a couple of examples. So the way we're going to look at those examples, we're going to read it together. And then you're going to pause and I will explain you the answer later. Some of those examples might be on exams, so it's very important to go through those examples a couple of times, try to make sure that you understand the difference between physical and logical independence. Okay, so first scenario. Um, I want you to tell me whether the scenario below represents physical or logical independence. So our scenario, company decides to separate a single employee table, the table that contains employee information, into two separate tables, employee personal information and employee work information, to better organize the data. So regardless of the structural change, applications and queries that work with the database can continue to retrieve employee information without need to modification. So this is an example of what? We need to analyze where the change is happening, okay? So this specific change is happening on the database level, right? And we remember that the database level, based on the previous slide, is an internal model, right? So now I'm gonna put a pause for a second and think, whether it's physical or logical independence. All right. So back to my explanation, employee table lives on the database management view, right? So it's part of the internal model. Well, we're talking here about changing internal model without changing how program access the data. And program that access the data sits on the conceptual model or up or down. So again, we're changing internal model without affecting conceptual model. That is going to be logical independence. And here's an example. So example here, pretty much very similar to the example, to the scenario we just looked above. So that would be logical independence, okay? Let's look at the next scenario. Next scenario is also, we need to identify whether it's physical or logical independence. Library changes its system to include new category for ebooks while maintaining the existing categories of physical books. So again, we add more data, okay? And we are dealing with the database, we're modifying the database, and we're adding more data, right? So think a little bit where the changes to the data happened um, on what level, and I'm gonna put me on pause here and decide whether it's physical or logical independence. All right. So that would be also logical independence because again, similar to the previous scenario, we are modifying internal model here, database management system view. We are adding additional categories. And with this addition of additional of the categories, conceptual model or routines that access the data that sit on the level of conceptual model or higher do not change. So that is also logical independence, okay? All right, let's go to the next scenario. Database administrator decided to switch from using traditional hard disk drives to solid state drives for storage purposes. Despite this change in the storage, the organization database remains unchanged, representing integrity and accessibility for users and applications. So same analysis here. First, we need to identify where the actual change is happening, on what level, based on the diagram on this page. So put me on hold for a second and think what would be the right answer for scenario 3. All right. So this scenario will be physical independence because we are modifying a physical data model, and this change to physical data model does not affect the internal data model. So internal data model stays unchanged. So that is the physical independence. Again, logical independence happens when we make changes to the internal data model without changing conceptual data model, and physical independence is when changes the scenario when changes to physical data model do not result in the required changes in internal data model. Right. So We talked about abstraction. We talked about logical and physical independence within terms of abstraction. So let's look a little bit about how different data models evolved over time. So somewhere around 1960s, the first data models created were hierarchical and network data models. Those were designed to store linear data. They didn't support the relationship between different data nodes. They didn't support structural independence. They were highly dependable on the structure. So they were a little bit better than a file system, but still they were not designed to support relationships between different data objects. So in the beginning of 1970s, there was a revolutionary step made in database development, and the person who made it was um, Edgar Cobb. Edgar Cobb is probably the most important person and pioneer in database development. He worked at IBM, and in 1971, he first introduced relational data model. He was feeling a lot of pushbacks from different parts of the company, from his co-workers. Relational data model was completely different from network and hierarchical model. It allows to build a relationship between different data objects. And those relationships were defined by multiple concepts that support those relationships. Um, it was much simpler than network and hierarchical model. It supported data retrieval language called SQL, which is still very alive and used. And it supported set-oriented access. So for those of you who took math classes, you guys are probably familiar with theory of sets. But in the terms of the database, set means it allowed to retrieve multiple data sets based on the certain criteria. Um, Further down, entity relationship model was developed. Entity relationship model was developed um, by scientist with the last name Everett. Well, actually, no, it was developed by Chegg. And further down, it was improved by Everett. So entity relationship model is a concept. It's a model that allowed to create a representation of the data model in the diagram. And this entity relationship model we still use as a main data modeling technique for creating models for relational databases nowadays. Then further down, there were additional data models developed. Those include semantic. Then semantic was split into extended relational model or object-oriented model. And further down, in 2009, we started developing more complex data models that further down supported big data databases. Um, in this class, we will spend majority of the time working with relational data model and entity relationship model. So for the entity relationship model, we will be working on that for the next two classes. Relational data model, we will cover bases during today's class in a minute or two, and then we will get back to relational data model when we will be creating our databases. So relational data models had four main components. Uh, Relations, keys, primary key and foreign key, and constraints. So, what are relations? Relations and tables are very similar terms. There is a difference between tables and relations. We will talk about those more in our class 5. But for now, we will agree that tables and relations represent the same thing. So they're used to store actual data. So each table has rows, as we know. Rows can be called record, tuples, and columns. Columns are attributes. Um, each row in the tables is unique. So each row represents a unique instance of a specific entity. Each column represents a specific attribute. Okay. Now, in addition to tables, it's very important to understand the concept of keys. So there's two types of keys. There is much more, but there's two most important types of keys in relational data model. It's a primary key, which represents a unique identifier of each row in a table. So based on the primary key, no two rows in the table can have the same primary key. So it's a unique attribute that uniquely identifies specific row. So for example, it can be customer ID in a customer table that uniquely identifies customer, right? So there is no two customers that can have the same customer ID. There is also a foreign key. Foreign key is a field or attribute in one table that links to a primary key in another table. So, which allows us to create relationships between two tables, and allows us to link two tables together. Okay. So tables, primary keys, foreign keys. Now, here is an example of table or relations. Let's look at that in more detail. So we have a customer table here. Customer table has stores information on four customers. So it has four rows or four tuples. It also has six columns or six attributes. Okay, so attributes would be customer ID, first name, last name, email, phone number, and address. Okay, in this case, customer ID is going to be a unique identifier of customer tables. So customer ID must uniquely identify only one customer. Okay, so it is a primary key. Okay, now we have tuple here. We also have attributes. So that's an example of very basic relations. Okay, so customer table has columns, attributes, customer ID, first name, last name, email, and phone number. Okay. Now, let's look on how the tables are linked in a relational data model. So, for example, in this scenario, we have an employee that works in a department. So on the top, we have a department table with department ID and department name. And on the bottom, we have an employee table that has employee ID, which is a primary key, first name, last name, email address, and department ID. In this case, those two tables are linked based on the primary key foreign key relationship. And those relationships are built via department ID foreign key that links to a department ID primary key. So relationships are built based on primary key, foreign key relationship. Okay. So that is how relational model link tables together. This is exactly the same representation, but in the form of diagrams. Um, in this course, we will be reading a lot of diagrams. So that is a very simple diagram that shows department table in the diagram format and employee. So each of those have a list of attributes and has different keys. So department ID is a primary key in department, and employee ID is a primary key in employee table, and employee table also has a foreign key to a department. So in this notation, we can see that a star near employee represents that one department can have multiple employees, but employee can belong to only one department. So one here represents that employee can only work for one department. Right. So that was a relational data model represented in the form of diagram. Right. Now let's look on how data is how to identify couple of examples on how relational how the data is related to each other in relational data tables. Let's look at this example. So we have two tables here, product and vendor, and we need to understand how those tables are linked together. And we have a couple of hints. Those hints tell us to look for columns with the same name in both tables. Also, looked for the columns that look or contain similar data. Guys, this example, we're gonna have a couple more examples, but this example is going to help you to work on problem one from homework one. So let's look first at columns with the same name in both tables, and then see if the data type in those columns is going to be similar. And if that's the case, that means that those are probably foreign key, primary key relationship, and that's how the tables are linked together. Put a pause here, think it to yourself, and I'm going to explain you how those tables are related in a minute. All right. So our hints tell us to look at similar columns in both tables. So let's look at the columns. So product table has product code, description, price, product hands-on, and vendor code. Table vendors has vendor code, vendor contact, vendor appearance, and the vendor phone. So vendor code is a column that exists in both tables. So most likely that is going to be our connection. But let's analyze the data first. So vendor code in vendor table, for example, has like 230, 231. And let's look at the vendor code in product table. So it looks like it's pretty much the same data. Okay. So most likely, that's how the tables will be related together based on vendor code. And if you look at the vendors table, vendor code is going to be a primary key in vendor table, and in product table is going to be a foreign key. Okay. Let's look at another example. So it's a little more complicated. We need to describe how how those three tables related. So we need to find common columns or attributes in those three tables. So Put video on pause, try to analyze it yourself, and we'll do it together in a minute. All right. So similar to the previous example, we are looking at columns that look the same in tables. So in this case, we have a product table that has supplier and category ID. Table categories has category ID. So most likely the link between categories and product is going to be based on category ID, right? And in this case, category ID is going to be a primary key in categories table and foreign key in product table, okay? Um, Similar to table supplier, you have a supplier ID here, which is a primary key in supplier table. And supplier ID column exists in both product and supplier tables. So supplier ID is going to be primary key in supplier and foreign key in product. Okay. And that's how those tables are related together. Again, try this example yourself. You will have very similar example in your homework one. So that is going to prepare you for homework one. Right. Um, so here's an explanation, word explanation on how to tables are related together. So table product related to a table supplier via column supplier ID presented in both tables. And here you give an example, supplier for product chai is exotic liquid, supplier ID 1. So that is how you write an explanation how tables related together, okay? Here's one more example. Based on the model, relational model represented by those three tables, we need to answer the question, can one category have many products? So we are looking at table category, column category, and we need to understand, can one category have multiple products? Put a pause on video, and I'll explain you in a minute the answer. Right. So, if you look at the category column on product table, there's multiple rows that have, for example, category one or category two. So, category one is beverages, and category one represented many times, multiple times in product tables. So chai belongs to category one beverage, chang belongs to category one beverage. Similar to category two, which is the condiments, we have syrup here, Cajun seasoning, and so forth. That means that one category can have multiple products. Okay, so the answer is there is three products that belongs to category one. So it's actually two. So one category can have multiple products. Yes. Next question. Can one product belong to multiple categories? Let's try to answer that. So the answer to this question will be no, right? Because if you look at, for example, chai product, you have only one category ID here for chai product. That means that, and similar to all other products. So category ID has just one number, not many comma separated numbers. So that means that one product can belong only to one category. Okay. So now, um, entity relationship, we looked at a relational data model, we looked at the component, we looked at a couple of examples, which is again going to be part of homework one. So now let's, the rest of the class, we will spend on entity relationship model and entity relationship diagram. So Entity relationship model is a conceptual data model that represents entities, attributes, relationships between those entities. Um, cons- Entity relationship model is represented by entity relationship diagrams. So we'll be drawing a lot of different diagrams. And when it comes to entity relationship diagrams, there's three different notations or the way to draw this diagram. And those notations include chain notation, obviously, for based on the person's name who developed it, cross-foot notation, and class diagram notation, which is the UML. So for those of you who are taking programming classes, you guys are probably familiar with concept of UML. So let's look at those notations. They all represent the same thing, but they look slightly different, okay? So chain notation, you can see, has those triangles and the rhombus in the middle, and well, there is also UML diagram. For this class, we will be using cross-foot notation. So cross-foot notation is a very clear notation developed by Everett. It's still used widely when it comes to diagrams. You will need to draw all your diagrams in cross-foot notation. I will not accept any diagrams that are not drawn in cross-foot notation. Please do not use chain notation or UML notation. All your diagrams must be drawn in cross-foot notation. Why it's called cross-foot? Because, well, it does look like cross-foot. So if you can look at this symbol, it's actually cross-foot. So let's look on how to read cross-foot notation. Um, there is a document in Canvas that explain you how to read cross-foot notation in details. Please look at this document and read it. It's called How to Read Cross-Foot Notation. Um, so there's four different types of relationship or symbols that represented here. You have crow's foot and one little vertical line. That means that relationship is required or mandatory, and it's many. So then you have the next one that has crow's foot and empty circle. That means that relationship is optional. So it can be many or zero, and mandatory it's one or more. Well, optional is many or zero. Okay. Um, there is also a vertical line and empty circle, which means it's one and optional. So it's one or no instances. And then it's one mandatory. There is two vertical lines. First one represent one, and second one states that it's one and only one. Okay. So let's look at our first example of entity relationship model, and let's try to read it. So we have three different, actually four different entities here. We have customer, orders, order details, category, preferred category, and customer address. So customer places orders. We can see that customer can place multiple orders, but it's not mandatory for customer to place orders because there is an empty circle here, which means that it's optional. Okay. Order must be placed by one and only one customer. order can have multiple, must have multiple details, but should have at least one order details, okay, and so forth. But that is a very first example of entity relationship model for online ordering system. Again, drawn in cross-foot notation. And if you ever need to go back and look at cross-foot notation, here's an explanation, and there is an explanation in Canvas on how to read cross-foot notation. All right. So entity relationship model has components, and the main components of entity relationship models are entity, attributes, relationship, and constraints. So what is entity? It's a person or an object or a concept of interest that we will be collecting data on. In the first diagram, we have two different entities, students and classes, that are related to each other. So student can take many classes, and one class can be taken by many students. Okay. Now, an attribute is a characteristic of an entity. So similar to relational data model where we have columns representing attributes, here we have attributes listed under the name of the entity. Okay, so students has student ID, student name, student's address, and class has class ID, class name, and description. And in addition to attributes and entities, we also have a relationship represented on the third diagram on the bottom. So relationship shows how entities are related to each other. There are three different types of relationships: one to many, many to many, and one to one. So in this case, we have many to many relationship because we have cross-foot on both sides. Okay, so it's many to many. All right, so those are entity relationship model components. And there is one more important component. That is a constraint. Constraint is a restriction that we add to data that explains us how data processes must be managed. It also helps us to keep data integrity. And in business, constraints are usually represented by business rules. So below are examples of constraints. So employee's salary must have values between 6,000 and 350,000. Good salary. Student GPA must be between 0 and 4. Class must have at least 2 lectures qualified, and so forth. So those are examples of constraints or business rules. Now, let's talk about business rules in more details. So what is a business rule? It's process, it's set of operational processes or procedures that each company has, and that's how the company or company department operates. For example, customer can place multiple orders. Customer must have only one account. Those are examples of business rules. So where do we get business rules? Collection of business rules, it's a complicated business process that takes sometimes years. So when we need to know business rules, we can communicate to upper, lower management, look at the policy documents, talk to interview different company members. So business rules are the most important part. Collecting business rules is the first and the most important part of the database design. So business rules allows us to create standards on how the company operates. There also, we talked about that models and business rules are a communication tool that allows different parts of the company communicate to each other. It also they're also very important for database development, and they help database designers analyze those business processes and create a database and further down the system that supports those that will be able to support the software developed to use specific database. When it comes to business rules, those are description of the good business rule. A good business rule must be declarative. It must tell you um, what, not how of organization. So, for example, lecturer can teach in multiple departments versus lecturer teaches classes in college. Well, the second one doesn't give us much meaning, doesn't allow us to create a relationship between lecturers and other entities. Good business rule must be clear and agreed upon meaning. It must be precise. So, example of that is engineer must hold at least one Microsoft certification versus employee hold certifications, which is not a very precise rule. A business rule must be atomic, must be represented by one statement, consistent, understood internally and externally, um, should be non-redundant, and most likely it must be business oriented. So good business rules are identified by asking question about who, what, when, where, why, and how of the organization. So all of those questions allows designers to collect business rules for future database development. You guys will be creating business rules as a first, actually second step of your team project. So that is where your team project will start. So again, business rules is where every database design starts, and that's what you'll be doing in team project. Um, let's look at the couple of examples of business rules and decide whether it's a good or bad business rule. I'm gonna pause here, let you guys look at those 6 business rules and decide for yourself whether it's a good one or bad one, and then further down we will look at each one, and I'll explain you why it's good or bad. Okay, so let's start the analysis. First one, an employee can be assigned to multiple projects without any limit. Is it a good one or bad one? Let's look back at what good business rule is. Declarative, precise, atomic, consistent, distinct. So I guess here we have a problem with the second quality, precise. So we don't have any limits, so it's not precise. So it's not a good business role. An employee can be assigned to a project. Is it a good one or bad one? It's not a bad, but it's not too precise either. So the next one, each employee can be assigned to a maximum of 3 active projects at a time. So this is a good business rule. It tells us minimum, maximum, and it is precise, distinct, and tells us enough information about 2 different data types, employee and projects. Next one. Projects have SKUs. So it's not a precise business rule, and it's not declarative enough. It doesn't tell us whether it's one SKU or multiple SKUs. Next one. Each project in inventory must have a unique SKU. Uh, this is a precise good business rules. So those two are good business rules. The other two are not so good business rules. For your team project, I want you to give me good business rules. Okay. All right. So let's look on how business rules are translated into entity relationship diagrams. For example, business rule, a customer may generate invoices. So let's look at this sentence. This sentence contains two nouns and a verb that connects those two nouns together, right? Customer may generate many invoices. So customer and invoice. Those are probably going to be entity. So for this business rule, you gather the following. Customer and invoice are objects of interest, right? And there should be represented by entities in the diagram. And there is also a generate relationship between customer and invoice. There is an additional rule that states an invoice is generated by one and only one customer. This specific business rule tells us that there is one-to-many relationship between invoice and a customer. So this is how we analyze business rules in for the entity relationship diagram creation. Okay. All right. So um now we're almost ready to draw our first diagram. Okay, we looked at two business rules, we analyzed them. So let's start. I know you guys haven't done the exercise for creating your for selecting diagramming tool. It's due this week, so you can draw with me on paper, or you can just watch me. And by the end of this week, you will be ready to for the next class when we'll be drawing the actual diagrams. Okay, so we have two business roles. So we're gonna work first with the first one in details, and then we're gonna add the second one. So customer may generate invoices. We know that nouns represents entities and verbs represent relationships. So we're gonna start with entities. Um, we have two nouns here, customers and invoices. So customer and invoice are entities. We're going to draw our rectangles for entities, and then we're going to start looking for verbs. We have a couple of verbs here. So we have may generate many invoices. So generate is a verb, right? So there is a generate relationship between customer and invoice. So we're going to connect our two entities, invoice and customer, together, and we're going to draw a line between them that represent relationship generate. Okay. Now, we have entities, we have relationships. Now we need to understand what type of relationship we have here. So let's go back and see what we have here. First of all, we need to understand whether the relationship is one-to-many and whether it's optional or mandatory. So we have word many here. So customer may generate many invoices. That means it's one-to-many relationship. So customer is a singular, invoices is a plural, many invoices. So we draw crow's foot on invoice side, and that represents many, and we read it from customer to invoice. So customer generates many invoices, many represented by crow's foot, okay? And one is represented by vertical lines. So invoice must be generated by customer. Okay, so we're almost done, but we still have this may word. May means the relationship is optional. So customer can generate invoices, but he or she doesn't have to. So customer can have zero to many invoices. So this empty circle represents optional relationship. Okay. Now, um, the only thing we're missing is whether relationship on customer side is mandatory or optional. So, well, there is nothing more we can gauge out of this rule. We can potentially guess that invoice needs a customer, so customer is mandatory for the invoice. So, but luckily, we have another business rule here that states invoice is generated by only one customer. And that last business rule tells us exactly what we need. So this means that only one customer must exist to generate invoice. So it's mandatory to have a customer for the invoice. Cost invoices are optional for a customer because of this may word, but because of the second business rule, we know that the customer must exist for an invoice. Again, that is a very simplified scenario. Majority of the real life scenario are not that simple, but that is our first entity relationship diagram. So congratulations, we just draw our first diagrams. Now, we draw the first diagram. Let's learn how to read those diagrams, okay? This is our diagram. So the only thing is, oh, and the difference between the previous diagram and this one, now we have word generate that actually represent relationship. So what is missing here? This diagram is very simplified. So we can see that we're missing attributes. So we're missing students. Oops. We're missing, for example, like here we have a student and class, and we have student ID, student name, address, and so forth. Same for classes. Our diagram doesn't have attributes, but again, it's just because it's simplified diagram. We're not too concerned about attributes just yet. Okay. Now let's create another diagram. Let's look at the previous diagrams that we created, and based on the example, let's try to draw another very basic diagram. Pause the video here, go back to the previous slide and see if you can draw a diagram for this scenario. We have two business rules here. Customer must have an account, and account belongs to one customer. Pause the video and then draw the diagram, and in a minute I'm going to show you the solution, explain you how I do this diagram. All right. So customer must have an account. So we know based on the analysis similar to the previous example, we have probably two entities here, customer and account, right? So we also know that customer must have an account. So customer and account, it's one-to-one relationship. So from customer to an account, it's one and mandatory. One because it's a singular account, and mandatory because of this must word. So we have one relationship on the customer side. We have two vertical lines, which is one and mandatory on the account side. The only thing we don't know whether whether it's mandatory to have customer for an account. And the second business rule is supplementary business rule that tells us that account belongs to one customer. So it's one customer and it's mandatory. Um, so simple, again, very easy diagram that is a representation of those two business roles. Another example, great, create. Another example here is two business rules. Again, please pause the video and practice interrelation diagram. Look at that. A lot of spelling mistakes. So look at that diagram, and I'm gonna pause the video and I'll show you a solution in a second. All right, so this how the diagram is going to look. So you have invoice can include many invoice lines. So invoice and invoice lines are two entities. Invoice lines is plural, so we can also have word many here. So there is a relationship between invoice and invoice lines that is many and one. So I would probably put it as an optional if I would only have this one business rule. But second business rule states that invoiced must have at least one invoice line. So it is mandatory to have at least one invoice line. So the relationship is mandatory here. Again, we don't have a single business rule that states anything about invoice line belonging to the invoice, but that is kind of self-explaining. So it's mandatory to have an invoice. Invoice line cannot exist without invoice. It must belong to something. So just like that, we did three examples of entity relationship diagrams. Now, let's try to combine all of those together. And voila, look at that. We just created a diagram that has four entities, multiple relationships. So again, creating an AR diagram is a complicated process, but if you split it into different chunks, different pieces of work, it becomes much easier. And it's an interesting process. So you go piece by piece, analyze business rules, then translate them into the entities and relationships, and as a result, you have a final combined diagram. All right. So we talked a lot about entity relationship diagram as a step for creating the database, creating the model. Now, there are scenarios, and those scenarios are very often happens in the real-time world when the database is already created or exists, when there was no time to create a design. So all of those scenarios are not the scenarios from this from a ideal world, but they do exist. So sometimes you need to look at the existing set of tables and create diagrams based on the data in the tables. You have in your first homework one, you have an example just like this. You will need to analyze existing tables and draw the diagram based on the data in the table. So, how you approach this specific exercise? Well, first of all, you need to identify how tables are related together, right? You need to identify the keys. And we already did this exercise a couple of slides ago, so you guys probably remember that tables, product categories, and suppliers are linked based on category ID in category table, which is a primary key here, to category ID in a product table, which is a foreign key in product table. And supplier ID is a foreign key in a product table, and it is a primary key in supplier table. So we also, couple of slides ago, answered a couple of questions, whether can one product belong to multiple categories? No, right? So product belongs to only one category. One category can have multiple products, right? Because here an example of category ID 1 that has chai and cheng, and category ID 2 has also multiple products. So one category can have multiple products, right? One product belongs only to one category, similar to a supplier. So one product can be shipped only by one supplier, but one supplier can supply multiple products, right? So product to supplier, it's a one-to-many relationship. And now we almost ready to draw the diagram, but we have one last question. So we know that relationships are many to many, so one category can have multiple products. We also know that relationship between supplier and product, one to many, one supplier can have many products, right? Now we are now we need to identify entities, right? So the entities would be product, category, and suppliers, right? Attributes for those entities would be columns of the product table, columns of the category table, and columns of the supplier table. You also know that one product can have only one category, but one category can have multiple products. So relationship between product and categories is going to be one to many, and many or cross foot is going to be on the product side. Okay, so we have everything we need for this diagram. I'm not going to draw a diagram for you, but that is an analysis that you will have to do when you will be drawing the diagram. Uh, and the very last questions that you will need to answer, whether relationship is mandatory or optional. Okay, so is it required for product to have a category? So let's look at the category ID. So category ID is populated for all the products, so it's never empty. So yes, every product has a category. Now, does every category has a product? So let's look at the uh, category ID in product table. So in category, we have total of 6 categories in the category table. 1, 2, 3, 4, 5, 6. Is every category represented in the category ID table in product? No, right? Only 3 categories are represented. So based on the data set that we have here, not every category has a product. So it is optional to have a product for a category. You will need to do the very similar analysis for a relationship between product and supplier. Let's look at the supplier table. Supplier table has total of 6 suppliers. But only 3 out of those 6 represented in supplier column in product ID. So suppliers 4, 5, and 6 do not have any product. So while it's required for product to have a supplier, because supplier is never empty here, not every supplier has a product. So it's mandatory for a product to have a supplier, but it is optional for a supplier to have a product. Okay, and now you guys are ready to draw the diagram, so you know your entities, which would be product categories and suppliers. You know the attributes, which would be columns in the tables. Uh, you know whether it's one-to-many relationship. After answering the questions, can one product belong to multiple categories and so forth. You also know if relationship is optional or mandatory. Again, based on the analysis of primary keys and foreign keys. So that's the analysis you will need to do for your first homework, question one. And based on your analysis and your rules is that you will record, you will draw your entity relationship diagram. Right. So again, sometimes as business develops, it becomes necessary to translate the existing database into a diagram. Now we learn how to draw the diagram. Now let's learn how to read the diagram. Okay. Um, Based on the diagrams that we drew a couple of slides ago, let's try to answer the question. So, can invoice exist without invoice line? So, we need to find two entities that we're dealing with. And here below here, I have cross foot notation so you guys can start using it or reading it. And again, I want to reiterate once again that there is a cross foot notation document posted in Canvas, so you guys can look at that. All right. To answer this question, we need to find two entities of our interest. In this case, it's going to be invoice and invoice lines. So the question is, can invoice exist without invoice lines? So we need to read the relationship from invoice to invoice line, right? And when we have a question like this, can invoice exist without invoice lines? They're asking us whether it is mandatory to have invoice line for the invoice, right? So we read relationship in the direction from the invoice to invoice line, and we read this with this second symbol, vertical line, the symbol that is further from entity. So the second symbol or vertical line in this case represents whether relationship is optional or mandatory. So in this case, relationship is mandatory. So the answer to our question is going to be no. The relationship is mandatory. So invoice cannot exist without invoice lines. It is mandatory to have an invoice line for each invoice. And again, how do I read it? I look at this cross foot notation on the bottom of the slide, and this relationship here is many and mandatory. And this relationship is mandatory, then it's required to have an invoice line for an invoice. Right. Let's read another example. The reason why I want you guys to get familiar on how to read diagrams, because you will be reading a lot of diagrams and it's also part of your homework. So that is where question 2 of your homework 1 starts. So your homework 1 has a total of 10 questions. You will be reading the existing diagram and answering questions like this. Okay. Now, next question. Can customer have multiple accounts? So similar analysis to as in the previous slide, we are trying to find in entities of the interest. In this case, it's going to be customer and account. And they're asking us, can customer have multiple accounts? So we are reading relationship from customer to account. And we are reading at relationship symbol on the account side. So in this case, we are reading on the symbol, which is two vertical lines, which again, based on the diagram below, means that it's one and mandatory, right? One vertical line means mandatory, and this vertical line that is closer to the actual entity, this line, means that it's one. So it's mandatory one. So can customer have multiple accounts? No. Customer can only have one and only one account. It's one and mandatory. We are reading the relationship from the entities that we are looking at to the next one where we need to identify the relationship. Okay. Let's look at another example. This one is a little more complicated. Can invoice be generated for multiple accounts? This one is interesting, right? Because we have a question that has two different entities that are not directly connected to each other, invoice and accounts, right? So we have an invoice here and accounts. So we need to kind of build a path from one entity to another. And we go from invoice to customer and then from customer down to accounts. Um, so um, First, we read it from customer from invoice to customer. So invoice can belong to only one customer. So it's one customer per invoice. And next, we are reading relationship from customer to the account. And it's also one account per customer, right? Because it's one and mandatory here. So it's one and mandatory here, one and mandatory here, and one and mandatory here, which means that it's one customer per invoice and one account per customer. So now we combine those together, and it means that one invoice can be only generated for one account. So when you have a scenario when two entities are not connected to each other, excuse me, directly, you just need to build the path from one entity to another one and then read it in this direction. And again, like, I mean, you will need to have the crow's foot notation handy so you would know what kind of relationship is that. But I promise you guys, in about by the end of the next class, you will know this crow's foot notation by heart. You would know what means what. It's pretty simple. It's just for four different types of relationship. So answer to this question is no, invoice can be generated only for one customer, and customer can have only one account. Therefore, relationship between invoice and account is one-to-one. Okay. Again, when entities are not directly connected to each other, you just need to have this planner pass from one entity to another. All right. So that's all I have for today. Um, So we start digging through more complex concepts of databases. Again, today's lecture covered the first two questions of homework one. You're ready to start on homework one today. Please do not procrastinate. Start working on homework one as soon as you can. And if you have any questions, please send them my way. Homework for the next week is to read chapters 2 and 3. Please make sure to read only material covered in this lecture slide. Chapter 2 and 3 has a lot of extra material. You're welcome to read through that or skim through that, but material that is not covered by lectures is not going to be covered by exams. So again, this is outside of scope of this course, but you're welcome to read everything. You're welcome to read about relational algebra, but relational algebra is not going to be covered in this class either. So you're welcome to skip it. So that's for today's lectures, chapters 2 and 3. Okay. For the next lecture as a prep, you will need to read chapter 4. Chapter 4 is for entity relationship diagram. It will help you tremendously if you read this or skim this chapter before the next lecture. It will help you to understand material better. So, assignment 1 is a non-graded assignment that asks you to select a tool for ER diagrams is due Sunday. I want to talk a little bit about this assignment. I want you guys to, I strongly recommend you guys to use Lucidchart. Lucidchart is free. Free version is enough for what we will be doing in this class, including team project. Free version also allows you guys to collaborate on the same diagram for multiple people, which is going to be very handy for the team project. But if you are not willing to use a Lucidchart, you're welcome to use any other tool you want. You also can use Google Draw. It's a little more complicated to draw diagrams using Google Draw, but again, if you don't want Lucidchart, you can do that too. I want you to create a simple diagram using the tool of your choice, hopefully Lucidchart, and I want you to post this diagram on Canvas under assignment 1. I think assignment 1 called homework A. So again, make sure to complete it by Sunday. You will need to know what tool you will be using for the next class. Next class, we will be creating entity relationship diagrams. So tool selection exercise, which is homework A or assignment 1, must be completed by end of the day Sunday. Homework 1 is posted. Please look at this homework. Questions 1 and 2 were covered by this lecture, so you're at a very good point where you can start working on homework 1 on questions 1 and 2. Questions 3, 4, and 5 will be covered by the next 2 classes. So again, don't wait till the last moment. Start working on homework 1, questions 1 and 2. Okay, there's total of five questions in homework 1. Homework 1 is due in a couple of weeks, but again, do not wait till the last moment. Homework 1 is somewhat large, so one day is not enough to finish this homework. And that's all I have, guys. So that concludes lecture number 3. I will have next lecture recorded for you guys at the beginning of the next week. You have good rest of your day or whatever time you're listening this lecture at. And now please start working on homework 1. And don't forget to do non-graded assignment by the end of the day Sunday. Talk to you next week.